I'm very happy to participate again to the conference after a few years that I didn't, and I'm very happy that we had a talk together with Anezina. So I very much enjoyed your talk. Probably I don't know many people that are connected, and I assume vice versa. So I would like to say that my name is Avdellidou, and I'm currently a postdoc at the Observatory of Nice in France. I will present our long-term study that is funded by an ANR, a National French grant, and that we do it together with Paris Observatory, the Lowell Observatory in Arizona, and the Southwestern Research Institute in Colorado. So one of the fundamental questions in planetary science is how did the terrestrial planets form directly from the protoplanetary disk? Today, we have reached a level where we can see the very first stages of the planetary formation in a numerous of protoplanetary disks around other stars. And also we can understand the results of the planetary formation era in our own solar system by studying our planets, but also by studying the thousands of exoplanets that we have now in the databases from the different surveys. However, the stages of the planetesimal accretion directly from the protoplanetary disk and before and sometimes during the formation of our planets is still hidden from our telescopes. So planetesimals were the building blocks of planets, and the small bodies that we see today, many of them are the relics of this planetary formation era. Now we have a plethora of small bodies residing in different locations in the solar system. We have the asteroid belt, the Trojans of planets, the centaurs, the Kuiper belt objects, but also the moons, as Anezina was talking before. And all these small body populations are not only in different orbits and locations in our solar system, but they have also diverse compositions. So here down on the right, you can see a card of the spectroscopic signatures of asteroids precisely. And this is the most used taxonomy nowadays, the one of Bass and DeMeo. And you can see that they can be quite different, indicating totally different mineralogy. So let's follow now some basic scenarios. First of all, we can have the formation of a bright planetesimal. Let's call them asteroids from now on, just not to get confused. We have a bright asteroid. Usually the bright asteroids formed probably in small heliocentric distances, and due to collisions, it may break and form a cluster of objects. So this cluster is created because the impact fragments, they have an initial velocity much less than 1 kilometer per second and places them in very close orbits compared to the parent asteroid. So the same process can happen in a dark asteroid. Usually these are formed in larger heliocentric distances. They may contain water or organics and migrated inwards during the evolution of our solar system. And also, of course, we have the planetesimals, the asteroids that survived intact up to now because no large impact destroyed them. As a result, the main asteroid belt contains all these clusters that I mentioned before, while inside they may still be hidden these lucky survivors. And if these dark and bright initial planetesimals are uniform inside their body, then their collisional fragments that we now call the asteroid families will look also homogeneous in their physical properties when we study them. Now, with respect to that, the homogeneity or not, there is another case. Some of the initial planetesimals, after their accretion, they were heated substantially internally due to the decay of the aluminum-26 and of iron-60. This heat led the object to undergo a thermal metamorphism, as we call it, creating layers with spectroscopic differences. In the extreme case, where the temperature that was achieved internally was high enough, then the heavier elements sunk in the center of the body, forming a metallic core. Then we have an olivine mantle, as you can see probably in this cartoon, and then we have the remaining crust. And probably this crust is made of this initial material before it underwent this metamorphism. This process is called differentiation. So this could happen in an early generation of planetesimals that they were formed big or not, but it still had large abundance of aluminum-26. And however, apart from nowadays, apart from the asteroid Vesta and its family, we have not detected any object that has strong indication, or it is definitely differentiated, or any other differentiated family in the belt. So the question is, using the asteroid families, what can we learn for the solar system? So first of all, we can link the known meteorites that we have in our collections with the asteroid families, because we need collisional sources in order to create meteorites and then send them to Earth. Also, we can pinpoint and study the distribution of the original planetesimals and understanding also how big they were formed. Also, we can retrieve the signatures of the dynamical and collisional evolution processes that happen in our solar system because they marked the small bodies of our system. And also we can look inside these bodies, understand by studying the families, understanding their material, and also their thermal evolution processes. Currently, we have orbits. This is a plot of the total main belt, and we have orbits for more than 1 million asteroids, and we have albedo data for about 140,000 objects. This plot shows the asteroid with measured albedos. The albedo distribution is more or less bimodal, with a separation for bright and dark, roughly around 12%. And we can see that even like this, it is very easily to identify some clusters like that, which are regions with higher density of objects. What are these? There are at least 120 asteroid families discovered so far, but still these are colored with the magenta color here, but we still see that the vast majority, the 3/4 of the known population, the vast majority of asteroids consist the so-called background. So currently they are not linked to families. The compositional signature of an asteroid is actually its spectrum. So previous surveys, they have produced data that helped to classify the objects in main complexes, and each complex is also divided into types. So spectra have the presence of, can show presence of bands, they have different slopes, and their combination with the albedo will help us to understand roughly the composition of the body. Now, this is exactly the same plot as before of the main belt, but the objects here are not colored with their albedo value, but they are colored with their spectral slope, as you can see in the smaller plot. And still, the asteroid families are very prominent. You can see these clusters. So the traditional method to identify asteroid families as clusters of fragments in the orbital space, so in semi-major axis eccentricity and inclination, is not perfectly effective. It is sensitive to young families, that their members are still in very close orbits, so these families are still compact, and they are more insensitive to old or very dispersed families due to resonances, but also due to the evolution in time. In this first plot, there are all the asteroids that we know in the inner main belt that have an albedo value. And the second, the panel B, is exactly the same location, the inner main belt, after we removed the families that we already know. However, we see that the methods that are traditionally used so far, that called the hierarchical clustering method, have not grabbed all the asteroids, but left out, you can see they create some rings. So these are the HelAS of the family. So we have two messages to take here. First, we have not identified all existing asteroid families in the belt. And second, where we identified families, the list of their members is very incomplete. And as I will try to explain in the following, this leftover background that we referred before are families that we haven't identified. They are the HelAS that we left out using the methods that we're using so far to understand them. And among these bodies, in between these bodies, they are the intact original planetesimals. So what we have to do is actually to deblend the asteroid belt. So there are several ways that families change. Due to the Yarkovsky non-gravitational force, the asteroids migrate in semi-major axis. If they are retrograde, they move inwards, smaller heliocentric distances. If they are prograde, they move outwards. So the smaller the size of an asteroid, the faster it moves in the unit of time. And therefore, if we plot the asteroid families in the space 1 over the diameter, and you can see in panel B, versus the semi-major axis, we see a shape that's like the letter V. So this, we call it the family V-shape. So the families have this characteristic shape. And here you can see a video how the prograde and retrograde asteroids, they move from its initial semi-major axis and migrate and drift inwards and outwards. So from these V-shapes, we can estimate the age of the family. A narrow V means a young family. It hasn't been dispersed so much. And a wide V indicates an old family. Now, let's go back to our initial story. So when we have a bright planetesimal, when the bright planetesimal broke, it made a family. When now the dark planetesimal broke, it made another family. So families can overlap in space, which makes it difficult to disentangle if an asteroid belongs to one or the other family sometimes. And therefore, we do need to have very good knowledge of the asteroid properties, which are their diameters, their albedos, and their spectra, in order to find also even small differences. So we thought to use this natural feature that the families do, this V-shape of fragments, in order to discover new families in the main belt. So I hope the video is playing. So by running the V-shape technique in a population of asteroids that we can assume initially they share similar composition, for example, albedo or spectra, we can discover new ones. As the method scans, it can identify the center of the family, and also the parameter that is on the y-axis, the C parameter, is directly linked to the slope of the V, and this indicates the age of the family. Therefore, by understanding the age of the family, we can also see when this big collision happened and produced it. Again,
5 more minutes.
5, great. Maybe. So again, this is the inner main belt. In 2013, our team discovered 2 dark asteroid families that you can see here. Maybe you can see here. I think I covered them. It's called the Eulalia and Polana. In 2017, we applied this V-shaped technique and we identified the primordial family that is as old as the solar system, meaning that this parent body broke very early in the history of the solar system. And you can see here the border is a dash line and it's called primordial. So everything dark could probably potentially belong to this family, but also the other 2 families, Polana and Eulalia, that they overlap in the same region. So the members of this primordial family cover, as you can see in your right-hand side, cover the entire inner main belt in the orbital element space. And this happened because the eccentricity and the inclination of its members was perturbed during the giant planet stability. So this family is so old that predates the giant planet stability whenever this happened. So the asteroid members of this family, the primordial one, they have very similar spectra that they belong to the C complex, they're carbonaceous, and we see also they have a peak in the albedo. This long tail in the albedo towards larger values is probably due to potential contamination from the background population, because we see that our primordial family, its V, is at the background that overlaps, as I said, with the Polana and the Eulalia. So maybe some asteroids, they are misclassified among these families. So the B panel of spectra shows the spectra that are in the region that overlaps with Polana and Eulalia. That's why probably we have more dispersion in the spectra. You see, it's more wide. So what we managed also to do by discovering this family was to literally pinpoint, you see in the red circle, the planetesimals in the region that are out of the view of the families. So what we believe is that whatever cannot be in the view of a family, whatever cannot be a member of the family, it should be a leftover planetesimal. So in green, they are also the other known low albedo carbonaceous families of the inner main belt, and we try to understand which of these families could be daughters of the primordial one. This means that it should be second generation or n generation of collisional events creating daughter families from the fragments of the original primordial one. So later in 2019, we discovered and published other 2 families also in the inner main belt. But this time, these families have moderate albedo values. They are not so dark. They are between 10 and 30% and belong to another spectroscopic complex, the X complex. Both of these families, Hathor and Zeta, are also very, very old. And we can see that by identifying the families and the family members, we can find also the planetesimals with squares also in this different albedo range. So slowly, we build the size frequency distribution only from observations of the inner part of the main belt. We correct the slope for different reasons, and then we try also to compare it with the theoretical values that we get from other independent theoretical models, and we see that we agree. For example, roughly speaking, planetesimals, at least observationally, cannot be smaller than, let's say, 30 kilometers in diameter. Now, and I finish now soon, to be able to retrieve at once all necessary data for a large number of asteroids, for a big population, this is something very important if anyone wants to do this type of studies. You cannot just go to literature and get one by one the data for thousands of asteroids that maybe belong to only one family. So therefore, we built here in Nice and maintain the largest repository of minor planet physical properties. And with this tool, this is the old page, now it is better, it's newer, but it's still not up. You can check individual asteroids if you want, or for a large group, or for a family itself, according to the search that you want to do. This tool also will be incorporated into VESPA from Paris, and this is all funded by the Europlanet. So I would like to leave you with my conclusions. And here, if I can say, I stopped here the presentation because we have a lot work done that is done about the last two X-complex families. We have done the spectral characterization. We have done a link with meta-rays. So we've done a lot of progress, but I'm not currently allowed, because it goes for publication, to present it, since our talks will be publicly available. So, but if someone wants something, we can also chat in person. Thank you very much.
Thank you very much, Chryssa, for the very nice talk. So now time for questions, comments to Chryssa. So please go ahead, speak up.
Chryssa?
Yeah.
Hi, it's Anazina.
Hello.
Great talk, thank you. I'm learning stuff I didn't know before, so yeah, indeed, thank you. What about the one that got your name?
This
you
one.
Mention that, because I don't know if everybody knows, so
okay,
it's important. Yeah.
Thank you. One sec. I cannot. How can I do it? Here, let's go here and let's play this one. Okay, do you see this slide now?
Mm-hmm. Yes, we do.
So by checking also with our awesome database of physical properties, I saw that this asteroid is small, is about 5 kilometers. So 5 kilometers is kind of high in this plot. If you plot in 1/d, okay, it's kind of high, and it's very dark. It's super black. It has 3% albedo, so probably something primitive carbonaceous, and technically speaking, currently is a member of the asteroid family of Polana. You can see here the V shape of Polana is between the Primordial and the Eulalia. So it is one, probably, because we have albedo values, so probably it is plotted in this. It's somewhere here, lost in space.
That's great. But so it's very dark.
It's super dark. It's
the albedo is up to 3.
It's 3. I think it's around 3%. It's 3%, if I remember by heart. It's about 5 kilometers in diameter, so it's small and dark. So definitely it's a fragment of a collision, and probably belongs now, because they overlap. You know, probably belongs to one of these families that probably comprise also primitive carbonaceous material that is not so much endogenous of the belt. So
very interesting. Okay, so now it has a name, and the name is Avdellidou.
It has a name. Yes.
That's very nice.
So yeah, we are happy. We are now 5 from Thessaloniki.
Okay, perfect.
So can you show us also if you can see in this plot the asteroid name after Athanasia Tollio and Giorgios Tsirvoulis? Can we see those?
I have to check where they are. One second. Unless Giorgos is connected and Sisi, unless they have already checked.
And Athanasia, yes, is connected too. So
So I have to actually, I have to stop this 1 second. And if you have time, I can do it. One millisecond.
Oh,
I have to. Am I sharing now?
yes, we can see your.
Bad. Okay. So this is MP Greek. MP. Right. I have to see the name of Sisi. Anesina, do you have it in front of you, the number of Sisi? Ah, no, because here is not updated by the.
No.
If someone can text me the.
What is it you need?
The number.
Can someone else help, maybe?
It was possibly in the newsletter. That
Yes, this is what I'm checking.
Yes. Newsletters. Yes, I will send you the link.
I have it in front of me. I just have to find. Okay, I found Servoulis. Okay. Sisi, you have to wait. I'm sorry. 28609, if I'm not mistaken. 28609. See. So Servoulis is a bit bigger. Okay. He's taller than me. That's good. It's diameter. Do you see my browser now?
Yes.
Okay. So you see here it's 6 kilometers, and the albedo is insanely small. Maybe, okay. Yeah. So it's about 6 kilometers and belongs to the family 2262. Which family is this? I don't think it is an inner main belt. No, where are you? Oh no, you're 2.6. So 2.6, he's in the central belt, because here is the resonance. If you can see, you see here is the resonance. So then Yorgos is in the central belt.
Okay.
So.
And how about Athanasia?
Athanasia, I have to find 1 second. Told you.
The number is 31873.
Okay, I found it. 31873.
Yes.
Let's see. So Sisi is a bit, is 4 kilometers. She is also super dark. She's also very dark. And she also Yorgos raised his hand. I think with Sisi, technically, we belong to the same asteroid family. Yes, okay. But we have to see more precisely, of course.
Yorgo, you are muted. Can you unmute yourself? Okay, thank you. And I think also Kostis has raised his hand, so please go ahead.
Something happened to my...
Okay, I'm sorry. Kosti, Yorgo, can you speak up now?
Hello?
Hi. Yeah, okay.
Go on, Yorgo.
Okay,
thank you. Yeah. Sorry, I couldn't unmute myself, and the chat is also disabled, so I couldn't help Krisa figure this out. So, but it seems you managed. Yeah.
Okay.
Yeah, it took me some time, but I managed. Okay. So, but here, this family complex of Polana has also other families inside, like Nisa, like Herta. They have different composition, but currently in the dynamic catalogs, they are as one family. But I think due to the albedo, as I see for Sisi and asteroid of Sisi and the other one of me, we are very dark and probably will belong to the same family. Yeah, Yorgos left. He went. Is it?
I'm middle belt.
Okay.
You're in another family.
Asti?
Yes, I want to ask a question just because you talked about the spectral characteristic of asteroids, and I remember it of Oumuamua, this object that came from another solar system, and I wonder if you know about the spectral analysis. Have we learned anything about it with the same methods? Spectral
About
methods about this?
Oumuamua.
Can you classify it inside the other object that you presented us? Is it possible?
I have no idea what is the spectrum of Oumuamua. We have an idea for the shape. It is very elongated and thin. So it's very weird shape. So probably it's for sure a fragment of something. It's not a primordial shape, this one. So it was not born like this, for sure. But about the spectrum, I don't know myself. Yorgo, do you know if they have a spectrum for Oumuamua?
I have no clue.
Yeah, this I haven't seen it, at least myself, somewhere. If they manage to get a spectrum of this object,
Okay, thank you.
be honest, but I can search for that.
Other questions, comments to Chrisa? I got one. So you are essentially dealing with a classification problem. So, you know, recently people have started to use some kind of machine learning schemes, tools in order to classify objects, including in astronomy. So have you tried, or do you think this may help for your tasks?
I see. Well, our job is more straightforward, to be honest. For example, myself, this is something that, as I said, I couldn't show, but maybe during the discussion we can say a few things. We have done infrared and visible spectroscopic observations precisely on the members of the families that we are talking about. So we produce also data. It's not only that we store them in the catalogs. These machine learning techniques that you say, I know there's another PhD student here from our group that he's tying in following these techniques to gather all the spectra that are currently in the literature together with the albedos and tries to see if with this type of techniques he can create another more evolved taxonomy compared to one that we are using now. But it's a general theoretical study. What we do is that we try to characterize specific sources, specific objects. But yes, what you say, yes, there are some other people that they try to produce new taxonomic schemes by using more type of data and combining them. This is something that was missing from Bas-de-Meo. So Bas-de-Meo taxonomy, we have a classification for their spectra, but we don't have, it's not directly also combined with the albedos, and the albedo is a very important parameter. Yes.
Okay.
Yes. The short answer is yes, some people try.
Okay.
Yes.
Okay.